Okay. Okay. So we are considering those maps. So we are looking for those maps from R2 to R2 which satisfies the distance preserving property. What does it mean? It means that suppose you have a map F from R2 to R2, right? So this means suppose this is your R2, the domain space, and this is your codomain space. Okay. So now you have 2 points. Suppose this is P and this is your Q. Okay. So these 2 points has a distance, right? Now what does this map do? So it will map P to some point FP and it will map to some point, suppose FQ, right? Now it satisfies distance preserving property means the distance between FP and FQ will be equal to the distance between P and Q. And it will be satisfied by F for all pair of points PQ in R2. Okay. So this is called the distance preserving property. Okay. Fine. So here distance means a map D on R2 such that for any 2 points P whose coordinates suppose it is x1 y1 and another point Q whose coordinate are x2 y2, we define d of PQ. I think you know this definition of distance, this one, right? x1 minus x2 square plus y1 minus y2 square and taking their positive non-negative square root, right? So this is the usual distance that we are working with, usual distance on R2. Okay, so this is your distance. Now if you think of R2 as complex plane, right? So we have seen that any complex number Z is actually a point in R2 written as Z equals to x plus iy and the point is this xy. So xy point is actually the complex number x plus iy. Okay. I can be denoted as 0, 1. This is the point. I is the point 0, 1, right? As you all know that xy can be written as, this can be written as x0 plus 0y. Now what is x0? X0 is a, can be, it will be identified to a real number x, right? So it is x0 plus, now 0y means it is 0, 1 multiplied by y0. Now it is known to you that complex multiplication looks like this. It is AC minus BD and AD plus BC, right? So this is your complex multiplication. So it is AC minus BD plus I AD plus BC. And with respect to this multiplication, you can see that 0y will be 0, 1 dot y0. So every, so if you identify any real number with the point x0, so identify x with x0 for all x belongs to R, then xy is actually, so it is identified with x, this one identified with x, this is your I and this is your y. So this can be identified with x plus iy, right? In this identification, you can say that every complex number is actually a point in R2 in a plane. Okay. Okay. And with this identification, you can write down the distance between 2 points in R2 as, so for PQ belongs to R2, you can write their distance as dpq is mod of p minus q. Okay, where mod p is actually distance between 0 and p, right? That is distance between the origin and the point P, that is root over x1 square y1 square, right? So this is the distance between origin 0 0 and P, x1 y1. Okay, right? Okay. And also, if we define the conjugate of a complex number z as z bar defined by z bar equal to x minus iy, or in terms of points in R2, it is x minus x comma minus y, where z is x plus iy that is xy. So this is your definition of conjugate. So conjugate means, so if you have z, this is your z, then it is xy, its coordinates are xy. So if you want to get the conjugate of z, then it will be, its coordinate is, so this is your x and this is your y. So what would be the minus y? In this direction, right? So it is your x minus y. So it's a reflection with respect to the x axis. Okay. And with the help of this definition, we have z, z bar. It will be x square plus y square. That means it is mod z square. So that is, mod z is root over z, z bar. Okay. So in terms of this one, you can also have the distance between 2 points as, so distance between 2 points, it can be written as p minus q, p minus q conjugate. Okay. 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 So we are concentrating on the maps from R2 to R2 that preserve distances, right, which are called isometries, right, which are called isometries. Okay. So informally, so formally speaking, the definition would be like that: the map phi from R2 to R2 is called an isometry, of the plane if for any 2 points PQ in R2, the distance between phi P, phi Q coincides with the distance between PQ. Okay. Okay. Okay, 1 minute, please. Okay. So this defines an isometry of the plane. Okay. So let us have a look some examples, some natural examples we are dealing with. Okay. So the first of all, so since it is a map from R2 to R2, so you would have the map identity, right? Now this identity will always preserve the distance because it will just take the point P to P itself. Okay. So for this one, so the identity map I. Okay. From R2 to R2 is an isometry, right? Okay. Number two, reflection about x-axis. What is that? Reflection about x-axis. That is the map F from R2 to R2 such that f of xy goes to uh, it is reflection about x-axis, so it will go to, so xy will go to, yes, x minus y, right? It is also an isometry. Why? Because, so take 2 points, suppose xy minus x dashed minus y dashed. Then what will have? So what you will have? So this will be, so mod of, it is x minus x dashed comma uh, okay, so it is minus y dashed. Okay, so that means root over of x minus x dashed square plus y minus y dashed square, right? So since it is a square, so minus y dashed doesn't make any difference, right? So this means it is x dashed y minus y dashed. So that means x y minus x dashed y dashed. Okay. So this proves that the reflection about x-axis is an isometry. Similarly, reflection about y-axis, that is again a map from R2 to R2 by the definition. So f of xy goes to minus x y. So you can easily check that this is going to be an isometry of R2 in a similar fashion that we have done for this case. Okay. Number 4. Number 4. So this is going to be a natural example, of an isometry which comes to our mind. Is a rotation. Rotation. What does it mean? That is, take any point. What does it mean? So rotation means, so take any point P. Okay. So then yes. So applying an angle theta, it will go to some other point P dashed, right? This way, right? This way. P goes to P dashed. That is a map. So rotation through an angle theta, about the origin, right? 0, 0 is defined as so it is a map from F from R2 to R2 such that f of xy goes to x cos theta minus y sin theta x sin theta plus y cos theta. Okay. So in this way you can define a rotation about an angle theta with respect to the origin 0, 0. Right? Now if you look at this definition very minutely, you will see that just that is f of, if you consider this xy as column vector, right, in this way, a column matrix, then you will find another beautiful observation behind this definition is that so f of xy, so it is x cos theta, y sin theta, x sin theta, y cos theta, right? So that means if you look at this matrix, you will see that this is actually cos theta minus sin theta, cos theta, xy, right? Okay. So these matrices are called rotation matrix. So that means this F is actually acting like this one. That is, it will take this xy to a point by acting this matrix, this one, and this is called the rotation matrix, right? Okay. Now it comes to our mind, it comes to our discussion very naturally, because whenever you are talking about complex multiplication, then you see that suppose we have two complex numbers, okay, two complex numbers z w, that is, suppose z is x plus iy and w is, suppose, x dash plus iy dash, okay. Then you see that the multiplication in between two complex numbers z and w is actually gives you some rotation matrix, okay. So how one does have this one? Just multiply z dot w, then what you will have? So it is actually x plus iy dot x dash plus iy dash, and if you look at the multiplication, so you will see that it is x dash minus y dash plus I xy dash plus x dash y. So in terms of column matrix, it is x dash y dash xy dash plus x dash y. So again, if you look at this matrix, you will see that it is actually the multiplication of x minus y yx with x dash y dash, okay, right? Okay. So this resembles with the notation that we have here. Okay, fine. So now we check that. So we check that any rotation is an isometry. That is, every rotation preserves the distance. Why? Okay. So just look at this one. Okay. Yeah. So let P is x plus iy and Q is, suppose, x dash plus iy dash. That means it is the point xy and it is the point x dash y dash. Okay. Okay. So then I have already written down that the distance between PQ is actually root over of P minus Q conjugate, right? Okay. So Okay. Okay, fine. So now, yes. So let us consider a rotation uh, of angle theta about origin. Origin 0, 0. Okay. That is, we consider a map r theta colon r2 to r2 such that r theta of xy goes to which one? Which one? With respect to this observation, how shall I write down this one? This is actually, this is going to be a complex number. What is that? Cos theta plus I sin theta. That means e to the power I theta, right? And it is your point. So it is e to the power I theta xy, right? So that is e to the power I theta xy. Okay. So with respect to this rotation, so what we shall get? So now we apply rotation to both these points P and Q. Then we see that, so uh, so d of P dashed Q dashed. P dashed is the image of P with respect to r theta. Q dashed is the image of Q with respect to r theta. So that means it is e to the power I theta P, it is e to the power I theta Q. Okay. So that means, so it is e to the power I theta P minus Q. Now what is the modulus of this complex number e to the power I theta? What is that? Modulus of e to the power I theta is 1. So it is PQ, P minus Q. That means it is d of PQ. So this proves that every rotation is an isometry. So hence every rotation is an isometry. Okay. Okay, fine. Okay. Right. Now, uh, so in terms of complex numbers, so, so any isometry from R2 to R2 can be viewed as, that is, suppose you have an isometry phi from R2 to R2, then we may regard this as a map phi from complex plane to complex plane, which preserves the distance. That is, phi of z goes to some u plus iv, that is, it is again a complex number, okay, such that phi of z, phi of w, the distance between phi z and phi w is equal to z minus w. So phi is a map from C to C which preserves the distance. Okay. Just we are thinking of these maps as maps from C to C. And nothing more than that. Okay. And then we show that actually our goal is to get all those isometries between R2 to R2. We have already seen some isometries, that is identity map, reflection about x-axis, reflections about y-axis, and rotations. Now we would like to characterize all the isometries from on R2. Okay? This is our goal. Okay. So along this line, so firstly, okay, yes, so then our goal, yes, is to characterize all the isometries of R2. Okay. So I don't want to give you the proof because maybe in later discussions I can give you the proof. I don't want to give you the proof at this time. So just I would like to write down. So yes. So the theorem is like that. Theorem. So if phi from C to C be a map such that phi preserves the distance, then you can prove that phi z is actually is either, it looks like that, alpha z plus beta, or phi z will be alpha z bar plus beta with okay, with mod alpha equals to 1. Okay. So this is the result. So with this one you can characterize all the isometries. Okay. Fine. So yes. Okay. Okay. And also yes. And okay. For some complex number beta. Yes. Fine. For some complex number beta. Okay. So that means, so this theorem says that any isometry of R2 is actually number one, either it is a pure translation, that means z goes to z plus beta, where alpha is 1, right? Right? Number two, a pure rotation, about uh, some center, right? Or if you regard this as 0 0, then you will find that z goes to alpha z, right? Or number three, a reflection about a line, that means z goes to uh, z bar plus beta. Okay, and another one is the last one, it's called a glide reflection. What is that? That is a reflection followed by a translation. That means z goes to alpha z bar plus beta. Okay. Okay, fine. Yeah. So we have seen that the isometries of R2s are one of these cases. Okay. Now I come to the case. So if we let I R2, what is I R2? It is the set of all isometries of the plane R2. Okay. Then we see that identity map belongs to IR2. It is an isometry, right? Also, if psi belongs to IR2, then what is phi compose psi? So this is again a map from R2 to R2 such that the distance between, so phi compose psi of some p, phi compose psi of q, right? So it is actually phi of psi p minus phi of psi q, right? Now since phi is an isometry, so it is psi p minus psi q, and since psi is an isometry, so it is e minus q. So that means phi compose psi, so phi compose psi belongs to IR2, right? And obviously the composition circle is associative, right? It is associative. Okay. Note that the identity isometry I plays the role of an isometry, or of an identity with respect to circle. So IR2 is a monoid with respect to circle. Okay, fine. So yes, so that means yeah. So this proves that IR2 forms a monoid with respect to the composition of maps. Okay, okay, fine. Now in okay, now we have already seen that we have already seen that if x be a if x be a geometrical figure, right? X be a geometrical figure in the plane, then the set of all symmetries. Now symmetries are special kind of isometries, right? Symmetries of X. Symmetries are the bijections from X onto X, right, which preserves the distance. Okay, okay. So if X be a geometrical figure in the plane, then the set of all symmetries of X, sim X, is a group, right? Okay. Now if we take x to be an equilateral triangle, equilateral triangle having vertices say 1, 2 and 3. Okay, that is, suppose you have yes, so suppose you consider an equilateral triangle. It is 1, it is 2, it is 3. Okay, that is, x is the set of all points on the perimeter of the triangle. This is the perimeter, right? Okay, so this is your set x, and we are looking for the symmetries of x of this. This is your x of this triangle. That means the bijections from x onto x, which preserves the distance. Yeah. Okay. So a symmetry of x should map each vertex to a vertex, right? A symmetry always maps vertex onto another vertex, right? Only each vertex to another vertex. Any symmetry will map. Suppose you consider this vertex, then it will map to either 1 or 2 or 3. To make the possibility of having distance preserving property, right? Suppose 1 maps to some other point. Okay, suppose 1 maps to some other points except these vertices, then it will not preserve the distance. Why? Suppose 1 maps to, suppose, here. Okay, so then, and suppose 2 maps to, suppose, yes, this one. Okay, then the distance between this point and this point will not be equal to the distance between 1 and 2, right? So therefore, any symmetry will map each vertex to a vertex only. Okay, and this observation tells you that we may identify the group sim X with the group with the group of permutations of the three element set of the set of vertices, that is 1, 2, 3, right? Okay, so actually the group of symmetries of this triangle results to the symmetric group of permutations with respect to this set of vertices 1, 2 and 3, right? So that means, so hence the symmetric group of any equilateral triangle is actually, it is S3, symmetric group of order 3. Okay. Okay. Fine. Okay. Now let us move to consider a square. Okay, that is x square. Okay, so then again you just take their vertices like that, like this way, 1, 2, 3 and 4. Okay, so then what you see, so what will you see? So okay, so the first symmetry will be the identity. So the identity map, the identity. Okay, next one. So next one will be, so let sigma, that is 1. Now we have seen that any symmetry will take vertices onto vertices, right, to preserve the distance, right? So let 1, 2, 3, 4, this cycle, so it will go to, so 1 goes to 2, 2 goes to 3, 3 goes to 4, right? So 1 goes to 2, 2 goes to 4, 2 goes to 3, 3 goes to 4. Then it will be again a symmetry. Just take a round around around this point. Just take a round. One round just. Okay. Then what is sigma square? That is 1 2 3 4 1 2 3 4 1 1 2 3 4, that is 2 3 4 1. So this is actually, so this is going to be 1 2 3 4. So here 1 goes to 2, 2 goes to 3, 2 goes to 3, 3 goes to 4, 3 goes to 4, 4 goes to 1, 4 goes to 1, 1 goes to 2. Okay. So that means it is 1 1 3 2 4, right? That is 1 3 2 4. Okay. Okay. So 1 goes to 3, 3 goes to 1, 1 goes to 3, 3 goes to 1. What does it mean? This point goes to 3 and 3 goes to 1. 2 goes to 4, 4 goes to 2. That is, what does it mean? And the next one is, okay, let us have a look at the next one. That is 1 3 2 4, 3 1 4 2, and again 1 2 3 4, 2 3 4 1. So what is that? So 1 goes to 2, 2 goes to 4, 2 goes to 3, 3 goes to 1, 3 goes to 4, 4 goes to 2, 4 goes to 1, 1 goes to 3. Yeah, that means, so it is 1, so it is 1 4 3 2. Okay, 1 4 3 2. That means, so in the previous case, sigma square, actually 2 goes to 4, 4 goes to, just taking a flip, right? And then take a flip out of this. And in this sigma cube, what we will have? 1 goes to 4, 4 goes to 1 goes to 4, just like that. Yes.
স্যার সিগমা স্কোয়ারটা বোঝা গেল না, বুঝতে পারলাম না।
Sigma squared, right? Okay. Okay. Yeah. Yes. 1 goes to 3. Yes. So what does it mean? If 1 goes to 3, okay. Achha, first one is 1, 2, 3, 4, right? That means, okay, just let me write down the sigma. Sigma is 1 goes to 3, 1 minute. 1 goes to 2, 2 goes to 3, 3 goes to 4. Okay. That means this is 1, 2 goes to 3, this is 2, 3 goes to 4, and 4 goes to 1. Yes. This one. This is your sigma. Okay. Okay. And what is sigma square? Sigma cube? Sigma cube is okay. Just take this one. How shall we get? So yeah. So okay, fine. Okay, this is your sigma. Forget about this one. Achha, okay, this is your sigma 1, and sigma 2 will be okay. Sigma 2. This is the rotation. This one is, yes, a rotation. I need to mention this. Rotation. Uh, Anti-clockwise rotation. Anti-clockwise about the center. This is your center through an angle pi by 2, right? To an angle pi by 2. Okay. 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 Yes. Now we make an angle pi by pi. So just take another rotation of angle pi by 2. Then what we will have? So what we shall have? So this is your 1, 2 goes to 3, 3 goes to 4, and this is your 4 goes to 1. Yes. Yes. Right? Yeah. Another rotation. A rotation about the center of angle pi. Sigma 3. Then sigma 3 is just taking another rotation of angle pi by 2 to this symmetry. This one. That is 1 goes to this, 2 goes to 2 here, 3 is here, 4 is here. That is another rotation about the center of angle 3 pi by 2, right? And then sigma 4. What is that? So it is 1 is here, 2 goes to this, 3 goes to this, this. Okay? So this is that means this is the identity. Right? Okay? So this is your identity. So you have, as of now, only identity sigma 1, sigma 2, sigma 3. Okay? Yes. Now, what is this permutation? Sigma 1? One, two, three, four. So at your 1 you have 4, right? And 2 goes to 3, 3 goes to 4, and 4 goes to 1, right? Now what is sigma 2? What is sigma 2? Just look at this. Here it is 3. This is your 3. That means 1 goes to 3. And this is your 1. That means 3 goes to 1. Okay. But so therefore here it is 2. That means 2 goes to 4. And it is 4. That means 4 goes to 2. So this is actually a rotation about the center of an angle phi. Right? Okay. Then sigma 3. What is that? 1, 2, 3, 4. So here it is 1. That means 1 goes to 4. Okay? This is your 2. That is 2 goes to 1. 3 goes to 2. And 4 goes to 3. So 1, 4. So this is the cycle. So 1, 4, 1, 4, 3, 2. 1, 4, 3, 2. And actually it is a rotation about the center of angle 3 pi by 2. And therefore ultimately you will have this sigma 4. It is a identity map. Okay? So are there any other symmetries? Yes, because R. What is R? R is the reflection. That is, suppose it is your square. That is 1, 2, 3, 4. And this is your center. And you take the horizontal line to the center. Now take a reflection with respect to this line. Then what you will have? So then this is going to be 1, 2, 3, 4. So what is the reflection? If you take a reflection with respect to this line, then 1 goes to 4, 4 goes to 1. And 2 goes to 3, 3 goes to 2. Right? That is, it is your 1, 4, 2, 3. Okay? Fine. Next one, V. The reflection about the vertical line through the center. Okay? To the center. That means this is your square and this is your center. You just consider this one. So it is 1, 2, 3, 4. And take a reflection with respect to this vertical line. Then what we will have? So this is your permutation. That is 1 goes to this, 1 goes to 2 and 2 goes to 1. 3 goes to 4, 4 goes to 3. That is 1, 2, 3, 4. Okay? Okay? Are there any? Yes. Yes. D1. What is D1? Just look at this picture. This is your 1, 2, 3, 4. And now you consider this one. This diagonal line through the center. Okay? So D1 is the reflection about the diagonal passing through 1 and 3, passing through the center 1 and 3. Then this D1 is 1, 2, 3, 4. So since this diagonal passes through 1 and 3, so they will be fixed. That is 1, 3 goes to 3. And you take just one flip along this diagonal. Just take a flip of this figure. Then this 2 will move to 4 and 4 will come to this 2. That is 2 goes to 4, 4 goes to 2. That means it is a 2 cycle to 4. And in a similar way, there is another diagonal passing through 2 and 4. 1, 2, 3, 4. So you have another diagonal. Right? Then this will be 2 and 4 are fixed. So 1 goes to 3, 3 goes to 1. That is 1, 3. Okay? So these are the symmetries of the square. So hence, these are the symmetries of the square. That is, it has, so sim of square is identity map, and then you have sigma 1, sigma 2, sigma 3. After that you have R, V, D1, D2. So it is a group of 8 elements. It is a group of 8 elements. And note that The symmetric group of order 4 has 4 factorial elements. That means 24 elements. So this group is a subgroup of S4. But in the previous case, the group of symmetries of the equilateral triangle coincides with the symmetric group of order 3. But in that case, you see that this group is a subgroup of S4, right? So this is called the dihedral group of order 4. And if you look this example minutely, you will see that since there are 4 vertices and a square is actually a regular 4 polygon, right? And for this reason, this group contains exactly 8 elements. That is, if you consider in general a regular n polygon and take their symmetries, then you can find out all the symmetries in this way, and you will see that there are actually 2n number of symmetries, and that will be called the dihedral group of order n, which has 2n many elements. That is, a regular n polygon, that is a polygon having n vertices, and it's a regular n polygon. Okay, then you can deduce that the symmetries, the group of symmetries of the regular n polygon has 2n many elements, and this will be called the dihedral group of order n. And in that case, the number of vertices is 4, so that is why it contains 8 elements. Okay. Okay. So with this one, I would like to end today's lecture.